we review it and present it on one very characteristic example. So the method itself, but let me first indeed to talk a little bit about the history, the Riemann-Hilbert problem. So the issue goes back to the last year of 19th century, so 21st Hilbert problem. So Hilbert, on the first International Congress of Mathematicians in Paris, formulated how many? 23, I have 23. A number of problems for 20th century, and this one is 21st. It is about kind of which we would call now inverse monodromy problem for Fuchsian systems. So let me just remind the setting. So we have n by n matrix equation. A of z is a rational function with only simple poles. I also would have at infinity also assume regular singularity, Fuchsian singularity. So the great fact about the global solution of this system is that every solution is holomorphic on universal covering of this function Riemann sphere, and this means that one can organize a quite fundamental thing. So having a system, we can define a monodromy representation of fundamental group to let's see. And how it works, of course, everything is extremely natural. So this is a base point for the group, and this is my points, A1, A2, so on. And so any loop gamma, having any loop gamma, you can organize, you start with the germ of the solution at the neighborhood of lambda naught. You organize analytical continuation over gamma. You obtain a new solution, which is of course should differ by the right multiplier. And so we get a map gamma to, actually usually they take inverse, so that it would be a representation, not anti-representation. So the monodromy group M of A of corresponding to my matrix, it is the image of this map of P1. Of course, I'm a little bit scopy, so you have to consider equivalence classes, but it is understood what should be done. And this is of course a finitely generated group. So M1, Mn, they are monodromy matrices that appears when you go along each loop around each aj. They have only one relation. And monodromy group, it takes care of all the global properties of my system. So this is a map from system to monodromy group, as we would call now direct monodromy map. And the 21st Hilbert problem was about inverse map. So this is whether there exists a Fuchsian system with given poles and given monodromy. There are, you can go to even Wikipedia now, of course, there are several versions of how, so several ways to translate what Hilbert said. So I stick to this one. It is taken from the very good book on Riemann-Hilbert problem. Yes, and this is what he asked, and this is what is the original Riemann-Hilbert problem. This is how it is. This is the Riemann-Hilbert problem in its original formulation. So it is very interesting to talk about this, the history of the problem. Well, I just name 3 key names. Bene, who reduce the problem to factorization problem of analytical functions to the singular integral equations. Very important. Then Prof, who introduced, it was somewhere in 57 maybe, who introduced the context of holomorphic vector bundle to the situation. And finally, the group who said no. So the answer is no. So that is, as I said, it is very, very, very interesting story, because for almost 100 years it was believed that Painlev solved it. But then it was found the gap in his proof by Kocher, Arnold, and Ilyashenko, and Bribrook suggested counterexamples. There are several different types of counterexamples, stable, not stable, so it's very, very interesting separate issue. Nevertheless, this was very important because it actually generated a whole area. So now, what we now understand by the Riemann-Hilbert problem, we understand a general question about reconstruction matrix, usually function, out of its piecewise analytic matrix valued function, out of its jumps. So,
can I ask a question? So each choice of capital AJ gives a different representation of the fundamental group. That's
well, this is this, as I said, you consider equivalence class. So the groups are considered. So if you conjugate the whole group, you get the same group. So.
Right, but they're different representations.
No, okay.
Okay.
No, maybe. Usually, of course, in concrete. So we're really working with this. As I said, this is a very interesting separate area, especially when you begin to talk about holomorphic vector bundles. But this is simultaneously, and this is what the message of my talks. It is that this is a very practical area. So we actually use it. So we actually use this thing. And in the practical things, we always have everything is fixed. We have always something which we can choose as a preferable choice of the homotopy basis. Yeah. But yes, but in the linear, well, it would be different representation in the sense that it would be the whole group would be conjugated. The conjugated by the same matrices. But it is natural to introduce the equivalence class with respect to this conjugation. So what is now understood as a Riemann-Hilbert problem is this. So you have a gamma, you have a contour, and a map from the contour to J and C. And contour, in fact, it is of course the original static, kind of the classical static. It is a line and circle, but it also can have some intersections. Very important. Something like this. And union of those, but you have to choose orientation. You have to choose oriented contour. And then it is oriented contour. And then G is maps. So this is a Z plane. So G maps Z to GZ. And the question is to find n by n matrix valued function yz such that it is velomorphic outside of the contour. It has plus minus values, so the boundary values from plus side and from minus side, which are related by the given z on the contour. And usually there should be some normalization. Usually it is at infinity, not necessarily, but this is more or less a standard setting. Of course, it is again very sloppy, so you should describe what in which sense everything is written here. And usually it is done again in each concrete case. This is what we are doing because we use these things as a tool. Or there is a whole area, the whole big area which been developed in the very deep and very interesting field about the boundary values of analytical functions. So when they analyze what conditional gamma, what are the weakest conditional gamma, what in which sense you can define plus and minus and everything would work. So this is a separate area which is extremely, of course, important and interesting. By the way, back to Hilbert problem. I can characterize what is a particular case. So the Hilbert 21st problem, it is a particular case, of course, of this setting. And how we create this particular case? We have, so again, this is my lambda naught. This is A1, say A2, A3, let's consider A4. So you have, this is a gamma, this is a basis, gamma to be basis, which I fix. This is a gamma to be basis. And now what I do, contour gamma, it is a polygon. It is a polygon. So this is a gamma. And what are the G? So here G it is just identity matrix. On this side it is M1 minus 1, so it is the monodromy matrix corresponding to this loop. On this side it is M1 minus 1 and 2 minus 1. In this side it is M1 minus 1 and 2 minus 1 and 3 minus 1. And that's it. So because there is a. So this is a Riemann-Hilbert problem which we have to solve if we want to solve 23rd Hilbert problem. So of course here the situation is that I have to describe that here it is the plus minus values are taken in a very, very continuous point-wide uniform manner outside of the vertices, of course. So I have to throw away the vertices, this means gamma naught. And I have to see what is going on inside near the vertices. It is the behavior. And this is where actually the data is. So if situation is generic,
equals to each of these matrices, or
G is piecewise constant.
no connection between G original and
G is what G is.
Yes.
Yeah, this is an example again. This is a particular example of the setting which corresponds to the 21st Hilbert problem. So if situation is generic, everything is fine. If situation is generic, you can actually transform this into behavior of this particular case, some constant matrix, velomorphic matrix near AJ, anti-diagonal matrix, related, of course, to the eigenvalues of the monodromy matrices, if you suppose that they are all diagonalized. So if solution exists, then it is easy to see that these logarithmic derivatives of y is a rational function with a simple poles, exactly as those vertices. And this is more or less how, so of course, and so this means that we have now to analyze this problem and Painlev suggested some integral equations, which one can write. And so kind of again in generic situation, although that this solution exists. Okay. Now, as I said, the theory was have been developed during whole 20th century, independently of solution of the Riemann-Hilbert problem per se, which, as I said, was thought that Painlev did it. So more or less until early 80s, nobody even had to come back. So it is a very beautiful theory, very subtle, but for our purposes, we would need just very few facts, very few, very general, almost classical facts. The first, it is Saplotsky. There are two transcriptions, of course, of the name Polish and Russian. Yeah. He was born in Warsaw, but spent almost all his life in St. Petersburg, and he died there in Leningrad. Formula. It is about Cauchy integral. Again, gamma when z oriented gamma. So this is the property of this integral. Important thing that under again the nice condition on gamma and on f, you would have good meaning of the plus and minus values of function. So of course it is analytical outside of the contour, and from the plus and minus inside of the contour, you would have plus and minus relation, which are given as this. So this is a supposed to be Painlev form. Not very difficult to prove if conditions are okay. But again, it is an interesting issue to see for how far we can, what functional classes would allow this relation. From this, in fact, it follows, very important, that if your Riemann-Hilbert problem is commutative, so if your jump matrix, for instance, n equals 1, or g equals triangular, like that, then of course the problem can be reduced to the analysis of the contour integrals. Then you can take logarithm. Then y would belong to the same kind. You take logarithm of this relation, and you would get that sort of explicit solution. Logarithm of g. Of course, again, I skip all the discussion on the analytical properties, index, facts, but the point is that we have this formula. And we can just the issue is to make sense to it, in a sense. If it is, by the way, if it is triangular, then it is just this. It is just this. Which can be just proven direct. To just reduce to this factor. So this is the second, and the third fact is that, of course, if the problem is genuine matrix problem, non-commutative, then you don't have integral representation, but you have integral equation. So it is not exactly linear equation, but it's close. So the solution can be actually written in the form of this integral integral, where this rho, so this is outside of the contour. Outside of the
There is a
contour.
class of matrices which don't satisfy condition 2 and still admit integral representation.
Huh?
There is a class of matrices which...
No, you're of course.
Yeah, yeah.
And I will be talking in
Yeah, but they said that if they not, then you have...
We continue. So rho z equals 1. Each speaker has its flag, you know. How to impress the... But of course the audience is absolutely, it's try to demonstrate its knowledge. Not satisfying. So rho satisfies. So this is already single integral equation. And indeed, seriously, of course it is. I will be talking a little bit later and even make a reference to Professor Antipov. So about indeed how this works. So this is kind of this C minus rho. So this C minus, it is a Cauchy integral, the single Cauchy integral. So this is C minus of f of z is 1 over 2 pi r limit z tilde goes to z from plus minus psi of gamma f of z prime minus z tilde. Okay. And there is one which we use, so the only so far all this is 19th century. But the fact which we use from the mathematics of 20th century, from infinite dimensional analysis, from functional analysis, is the fact that this operator is L2 bound, which is, of course is clear when it is line, when it is circle, but when it is has self-intersection, it is a delicate issue. Actually, it was proven somewhere in the late 70s, beginning of 80s. It's not quite. And this is these three things which basically we use, or more exactly, with basically which is needed for a problem related to Painlev equations, to orthogonal polynomials, to finite dimensional problems. So when we are talking about PDEs, then we have to, of course, to use more sophisticated ones. Okay, so that is the last remark which I want to say is that that one can think about matrix Riemann-Hilbert problem as a non-commutative analog of contour integral. So matrix Riemann-Hilbert problem, it is non-commutative, of course, non-commutative if G is not this, non-commutative analog of contour integrals. And in fact, if you look at this solution, you can see that I can find from this equation the following relation. It is minus 2 pi I limit as z goes to infinity, z times 1 to z. Trivial. And this is this jump matrix. So if jump matrix is triangular commutative, then we have this formula for the just contour integral of G. Except for slight fun, we can take this as a definition of contour integral. You can start teaching complex analysis and say, look, you have you just defined contour integral according to this formula, where y is a solution of Riemann-Hilbert problem with this jump matrix. Yeah.
Maybe pedagogically it's not the best way to do it.
Maybe not. But actually it is a good. So of course the cheating kind of conceptual cheating is that if I don't have the definition of Riemann integral beforehand, I don't know that this problem is solvable. So I can of course define I can define the Riemann-Hilbert problem. I do not need integrals, just analytical functions, and just boundary problems. So I can define the notion of Riemann-Hilbert problem without any integrals. Just analytic function does not need integrals. No Cauchy formula, nothing. And then I say that okay, the contour integral is undefined in this way. So logically everything is okay, but that's the question. I need existence of solution. And to prove existence, I need Riemann integral. I need this formula. I need this formula. But nevertheless, it is a fun just to use this thing, to calculate all the integrals which we calculate by residues. You just have this UG. I don't have, okay, if I have time, maybe tomorrow. It is a fun. So you just how to integrate, any rational function. You just write this and begin by hand factorize it to the up and down. And then you get of course the answers. So you can derive the residue theorem using this. So all of that. Okay, so now Riemann-Hilbert method. So now all this is about the Riemann-Hilbert problems. Now the Riemann-Hilbert. Now the Riemann-Hilbert method. So the idea is that having a problem, we try to reduce it to a particular Riemann-Hilbert problem, and then solve it. So this is the method. This is a scheme. This is a scheme. So the classical version of this scheme, it is Wiener-Hopf method in linear diffraction. And this is where what Yuri mentioned is very relevant to mention. So here again, this is a situation where very non-trivial linear diffraction problems reduce to the matrix Riemann-Hilbert problem, but of course matrices are concrete, with some concrete functions, some concrete entire functions in it. And then you just factorize it by Hopf. And indeed it is possible to factorize certain matrices which are not commutative. And this is how you get result. In a sense, it is all the non-trivial problem in diffraction more or less solved exactly by this scheme. So that is of course the classics. This is of course the classics. Nowadays there is a kind of second life of these classics, and indeed, due to Thanasis and due to Yuri, I would say. So they indeed kind of start solving problems, linear problems, which before were not attacked by kind of more sophisticated versions. The version which is much closer to what started at 70 plus. So at 70 plus, the new number of the problem fell into the realm of the Riemann-Hilbert problem. And they came from, first of all, they came from integrable system, from integrable PDE of KdV time and integrable OD of Painlev time. And the important difference, kind of philosophical, kind of conceptual, methodological difference is now most often those problems cannot be solved. you cannot factorize. You cannot factorize them kind of in any known functions, usually what appears, especially in PDE theory. In Painlev is the same. In Painlev is the same. But what it turns out you can do very effectively asymptotics. And this is where the modern version of Riemann-Hilbert problem is really works. So it really works. So there is even the term nonlinear steepest descent method. So it was introduced by Joe in the beginning of 90s. So just like in the classical steepest descent method for integrals, you look at the analytical properties of your jump matrix, begin to deform contours, so that usually it is you have some parameters, physical parameters, oscillatory dependence of G of these physical parameters. Go to the situation where the jump matrix becomes close to identity. And then your asymptotics would be represented by some local parameteristas that appears on the way of your deformation. And the non-commutativity brings much new ideas which were not here. So to those parameteristas you really want to solve explicitly. And this is where again appears non-commutative Riemann-Hilbert problems, but which can be solved in special functions of hypergeometric type, or algebraic geometry theta functions. So this is where non-commutativity makes the difference comparing with the standard steepest descent. And the very last kind of beneficiaries of the Riemann-Hilbert problem came from orthogonal polynomials. And through orthogonal polynomials, it is random matrices, enumerative topology, exactly solvable quantum field models. And this is what more or less I'm going to talk about next. So I'm going to now to present as a case study this thing, and solve what means asymptotic solution for the very classical object, for Topelitz determinant. So now it is the end of the introduction, and I start doing Topelitz determinants. So second part of my talk. So I have to introduce the object. I have to remind to introduce the object. So we have a C. I would denote the unit circle. It is a unit circle oriented positively. There is a function. It is a single scalar function. Usually it is enough to define Topelitz determinant, not just to have it L1. And then I introduce the Topelitz matrix generated by this symbol and by a matrix. This is just this. This is just this matrix, where phi k is the Fourier coefficients of symbol. This is the usual. Okay, it can be written, of course, as 1 over 2 pi, 0 to pi, phi p I theta, e minus I k theta, d theta. So the Fourier coefficient, this is right. So this is diagonal constant matrices. And what we are interested in, it is about the determinant. So the object of interest is this determinant of T. The question to address is its behavior. Of course, for finite n, it is a kind of explicit formula. For finite n, it is elementary things which involve just quantum. So this is a classical question, and in applications, more often you have dependence on many physical parameters, and what you are really interested to find, it is some double limits. kind of t goes to some critical t, and so then simultaneously as n goes to infinity. So this is the object, this is a question to address. Now applications. Now what importance of this object? Well, there is an intrinsic importance from the point of view of operator theory, because it was Toeplitz operators, it is when n is infinity. And this is a truncated Toeplitz operators, and so if you know something about some delicate things about these limits, then you know, for instance, some fine structure of spectrum of big Toeplitz infinite matrix. But in physics, it is even more kind of important, so to say. So of course, the main it is statistical mechanics. Statistical mechanics, and especially Ising model. So that was the whole kind of great story about that when it was found out. So first, of course, Ising introduced the model as a solvable. Introduced the model. Onsager solved it, calculated free energy, and then together with Kaufman they calculated magnetization. I will tell a little bit more about it. And to calculate this magnetization, in fact, they have to calculate some limit of the particular specific Toeplitz determinant. And by that time, what was known about Toeplitz determinant was the ciary theorem, 1915. But it was not enough for their purposes. And so the strong ciary theorem was born. So it is the second area as well. Again, Cn to T infinity. Let me just. And now, of course, there's the random matrices. Random permutations, random growth products, growth processes, enumerated topology. So many, and it grows. So it is going on. Now, what are the classical facts? What we know? What are the classical facts about Toeplitz determinants which we use? So classical facts. So now it is a set about the classical facts. What are the classical facts? First of all, there is this multi-integral formula. Toeplitz determinant can be represented as this. And integral, this is van der Waals. Okay, so that is a very classical also formula. Not very, it is of course does not solve the problem at once, because again, n goes to infinity, here it is the size of the matrix, goes to infinity, here it is the number of integration. Still very useful, and it is used in the modern, in the Riemann-Hilbert approach, but it is just a classical fact. The second, which is kind of I would use more, it is the relation to the orthogonal polynomials on the unit SOC, that is Barry Simon invented this abbreviation, OPUS. Orthogonal polynomials on the unit SOC. So, it is a polynomials, monic polynomials. Let me define two sequences of monic polynomials. So they are defined as p minus k 5z dz 2 pi I z. Y goes to 0, to n minus 1 it is 0, and when it is n, it is some norm. Okay, so this is a, and the second sequence, yes, and so in fact, this dm, it is not very difficult to show, it's just a product. Just the product. You can do better in sense of relation. So you can introduce the second sequence, which kind of dual. It is introduced in such a strange way, which will be clear why it is in a 2 minutes. Again, there's orthogonality to all powers beyond that in such thing. Hn. Of course, a priori I have to put some other h, but a posteriori it is the same. It is clear that those polynomials of course related to the Toeplitz matrix, because what should be determined? It should be the coefficients of these powers, and for them you have just linear system whose matrix is Toeplitz matrix. So that's not surprising that is this relation. There is of course the relation. So these are also, it is good to notice that these polynomials, there is this orthogonality. Now it is all up and down. And the last kind of formula that P of Z is P of Z, P Z. So it can be seen that this is this relation. So it means when we are so far I assume about phi nothing. Phi is complex varied function. Nothing is assumed. So they might be not exist. So my Toeplitz determinant might be 0. They might be. Huh?
It's no phi there in the second iteration.
Oh yes, thank you. I always forgot it. Yeah. Yes. So they are. They might be not exist. But in a classical situation, we have phi real variant, phi equals phi, and then everything exists. And then, of course, this relation, then this is just, and then this relation just becomes usual orthogonality relation for Pn times Pn complex conjugation, phi z and dz equals this. So then it becomes the classical orthogonal polynomials on the circle. How they are related to Ln. So this is maybe the last. Formula. So first let us change phi to phi gamma equals 1 minus gamma plus gamma. So let's organize the line, the straight line in the space of symbols from 0, gamma from 0, 1 to 5. Kind of join, right? And we assume that everything is great and exists for all gamma from 0 to 1. Then there is this formula. C Pn Z prime Qn minus 1 over Z. I cannot explain what is here. Qn minus 1 prime Z minus n Q of Z minus 1 to pi I dz. Here Pn of z. It is again something about something like complex conjugation. It is this. Take Pn, take it z minus 1, multiply by z, and I again have Pn. So this exists. So all Q, phi is phi, and P and Q, they are defined by this figure. Now, what are the classical results about asymptotics? Well, so under the good conditions, which are now kind of formulated, there are optimum conditions under which this asymptotic has. Dn behaves as e to z and d naught times plus k dk d minus k. What are the most important condition? P of z is not 0 for all z on the surface, and its index is 0, so it doesn't get argument from the whole. Then it means that phi of z can be written as e to the v of z. If those guys we denoted with just the Fourier coefficient of this v, or Laurent coefficient. Phi of z, zk, vk, k or minus plus infinity. So this is strong Seeger theorem. Plus. And then goes to infinity. So that is again long story. As I said, there was first kind of weak Seeger theorem without this term. So just only leading behavior. And that was not enough for Onsager to calculate that magnetization. It was very important to show that indeed. Yes. And then in fact, Onsager and Kaufman themselves, they actually calculated for their symbol. For their symbol, they actually calculated. So they found the answer. But of course, there was an exchange. I forgot exactly what the exchange was. And Seeger started thinking about it, and he proved it. But he proved it under conditions that phi is real, positive, and analytical condition Lipschitz of the derivative. So in some sense, it was very funny, because for Ising model, phi is complex. So what Seeger proved was not exactly can be used. And only in 1989, by Kurt Johansen, it was proven for complex phi. But the other, of course, great names are Ilyashenko and no. I'm sorry. Completely out of. Yeah. No. Ibrahimov, of course. Ibrahimov and Galinsky. So Ibrahimov actually kind of proved. So Ibrahimov proved, Galinsky proved the theory in 70s somewhere under the condition when it makes sense. So if phi is such that first of all indeed this v exists, and this sum also exists, is not infinite, then it's true. So this is some sort of course, of smoothness, but not very smooth. So it is just you have to. The second is when you have singularity. It is Fisher-Hart. Fisher-Hart singularity. So the simple case, it is you have CGO part, you have CGO part, and then you have, say, at one point, we put it in 1, it has, this is just not very important, it has root singularity, and it has jump. So at one point, you have root singularity and jump singularity. This would not exist, this would not work. Was that, and this is the CGO part. And the asymptotics in this case is this. First of all, of course, we have Z, which comes from CGO part. Then important thing that we have Paul-like behavior. Paul-like behavior. And then a quite non-trivial constant. So it is times E minus alpha minus beta vk minus alpha plus beta. Kind of influence between CGO part and Fischer-Hartwig and pure Fischer-Hartwig product of Barnes functions. Barnes functions. So this is asymptotic. This was also a separate story. So there was a conjecture by Fischer and Hartwig, and also Leonard wrote something like that. Then it was proven for several cases. So actually, again, this is of course the interesting case when you have several points. So the key names are Wiedem, Bazor, Botcher, Zilberman, Erhard. I can advertise our paper with David and Krasovsky, big review paper in Annals, when the history is presented, 2011. The history. And then there was also our paper about the Topelitz determinant under the influence of Ising model, when all the things related to the Ising model. So I can give the more example. So now what I'm intending to do now, it is just to, so the program minimum is to show how one can use the Riemann-Hilbert approach, which I have not introduced yet with the Topelitz determinant, to get these results. And also the program I won't have time. The interests of that Riemann-Hilbert program can do, which is much more difficult for classical methods, it is to discuss the transitional regimes. So we can consider the situation kind of extra parameter when we would have the Fischer-Hartwig asymptotics. Fischer-Hartwig kernel originally it is smooth, it is CGO type, and then the singularity goes to the unit circle and it becomes this one. And so there is a transitional asymptotics, which is described by the fixed linear equation in this case. And this is, by the way, it is our 2012 paper with Krasovsky's place, and it is actually the particular case of this situation was first considered again in the Ising model by McCoy, Tracy, and Wu. When the same question arose. So the Onsager Kaufman formula was for the temperature less than critical and upper than critical. And the question was what is going on when T goes to critical temperature. And this was, I believe, the first time, maybe the second time, as the Painlev equations appeared in application of mathematical physics. In the last three particular cases, actually Painlev 5 again. So this was in 1970. Simultaneous, so that was the story. So now let me, so that's the problem. I more or less I formulated the problem. So I formulated what are the Topelitz determinant and what is the question. And now let me do the first arrow in my Riemann-Hilbert method diagram to set the relevant Riemann-Hilbert problem for it. And this is where we will need orthogonal polynomials, which I introduced, which I erased. Okay. P and Z minus K, Q of Z, dz 2pi I Z equals 0. This is what I would use. And Pn hat Z minus 1 Zk Q of Z 2pi I Z equals 0. These relations. So let's define the following function. 2 by 2. First it is Pn of Z, and then I have this Qn minus 1. So this is the first column. And the second column is Cauchy transform of the first column with this density. With this density. Okay. Now, the proposition. So let's define this object. The proposition. So this Y solves the following Wiener-Hilbert problem. It is analytic outside of the units of the circle. It has, I would assume that phi is good. Jumps, which are triangular. And at infinity, it behaves as 1 plus O of Z, Z to the n, Z to the minus n. So I claim that this object satisfies these three props. So this is a particular case of Riemann-Hilbert problem. Some a little bit not traditional, but very important difference. Not traditional, not standard. But it can be easily transformed to the standard, and I will do it in a few minutes. So those two properties are absolutely trivial. So this is, of course, this one is you outside. So this is polynomial, this is the Cauchy transforms outside of the C. Now this jump, it is easily derived through the Sapolsky-Primel formulas, of course. So that's just Sapolsky-Primel formulas applied to the second column. The more interesting thing is this. This is where we have analytic, necessary these conditions. This is where we have these conditions. And this is, I just show, so you see what it means to have this condition. It means that you have to have here something which behaves as Zn minus 1, which we have for free. It is for any polynomials we will have this behavior. And here we would have O of Z minus n minus 1, Z minus n plus O Z minus n minus 1. So this is, of course, this second column is, of course, would not be true for any P and Q if we just take some empty polynomials. Because what we have, for instance, for y1, 2, for y1, 2, I can write it as 1 over z k plus 1, k from 0, and then I would have 1 over 2 pi I, Pn z prime minus n plus k, d phi and bz prime. So I just expand this denominator in the geometric series. So this is convergent series, everything is okay. And of course, everything from 0, 1, until n, I put it 1 and divide by z prime. Until n, all these terms are 0 because of the orthogonality condition. Because of this condition, all such terms are 0. And so we indeed have this behavior. N minus 1. So we indeed have this behavior. And similar, if you consider this, you would get this behavior. So that is a statement. And now proposition 2. Now proposition 2. Now proposition 2. So those, let's call them properties 1, determine y of the unity. And this is where everything plays. That multiplication is mostly on the right, and this behavior is also on the right. Because if I have, so first of all, I notice that if y exists, then its determinant is 1, identically 1. If you take determinant, then the determinant for g is 1, and so you have a function, determinant of y is going to be a function which does not have jump, and which behaves at infinity as 1. So it is identically 1. Now, if I have another solution satisfying all those properties, and I divide it by y, now it is okay to do because the determinant is 1. Then my R would be analytic everywhere outside unit circle, everywhere inside, and on the unit circle it would not jump, because the jump matrices on the right side, they would cancel. And at infinity, again, the same, because I have this bad behavior at infinity to the right, it is also would cancel here. And I would have that R is identically 1. So this is a and now we come to the methodological leap, and to the important methodological step. Now we are going to use. Now we are going to forget about this point. So now we defined y just as a solution of this equation, and orthogonal polynomials would be just given by those formulas. I have unique solution, and just my Pn and Qn are reconstructed from the first column of this solution. And of course, for instance, my Hn would be reconstructed from the, well, this I just remember that one, would be reconstructed as a y to 0. So this is also object of the Topelitz determinant, and now I can use that formula for the logarithm dn, which involves just those y's. So if I can solve this problem with gamma introduced, then I'm okay. And what is the great advantage of this? Because now, if before n in the determinant was just the size of the matrix, or the number of integration, now n it is just a parameter inside, so I nothing changes. I only have to take into account this what to do with this set. What to do with this set. And I am now for the, yes, and I would just have time to produce, I hope, partially the answer for the strong figure theory. So this formulation of orthogonal polynomials belongs to the Mike, Dave, Johansson. They formulated in 19. They used it in 1990, but also it is similar to what we've done with Thanasis and Kitaev. In 1992, for orthogonal polynomials on the real line, OPR, for the real line. So that was the first similar type of formulation for the orthogonal polynomials on the real line. And by Dave and Johansson, they kind of write similar things for orthogonal polynomials on the circle, and they use this formulation to solve long-standing problem of asymptotics of the longest increasing subsequence in the random permutations. That was a big thing. So now, so what we're going to do now, I am going to demonstrate how the Riemann-Hilbert technique works. Okay. So how I am going to solve asymptotically this problem. There is one, of course, deficiency of the Riemann-Hilbert scheme. I have to assume much more about the weight than usually in the analysis people do. But again, it is a method. It's just like Stipe's descent. You always have concrete function phi, and it is always kind of algebraic functions usually. So you can, in other words, the situation with Séguin, to prove the Séguin theorem, I would assume that of course that phi of z does not have indices, and it is analytic in an annals. So this is unit circle. So phi of c is analytic in an annals. There are also things that when you prove it for that, you can by some rational approximations to prove it for more general phi is the given one. But this is important too. But after we assume this, everything looks very simple in a sense. So first of all, so now I'm going to describe a sequence of transformation of this problem, which eventually would lead to the problem with a closed identity jump matrix. And then it would be kind of the end of the story. So first of all, the very simple. Y to t. So now already for about 20 years there exist these notations. So this is a problem which is, I'm just doing a very natural thing. I'm just moving this behavior at infinity to the jump matrix. So I decide that this is a z minus n. Sigma 3, it is 1, 0, 0, negative 1. So it is here. Z to the n. When z is greater than 1, and just identity matrix if z is less than 1. Then what I would have for t, I would have for t, I would have this, I would have that, I would have t minus. Actually, this z would be killed, but in fact it would appear here. The n, z negative. And y already would be just, because it is a contour is c, y exists at input of infinity. So this is already absolutely standard setting. And it is not commutative, basically. But of course it is explicitly solvable in terms of orthogonal polynomials, which I ordered to forget. Okay. So now we have oscillatory problem. So these guys are highly oscillatory terms. And I wanted to transform them to the exponentially decaying. Yes?
Sorry, this first condition, is there not a pole now?
Huh?
Is there a pole now at 0? So when it's
No. You see, I already do it.
Ah, okay.
Yeah, that's the point. This is a good question because, for instance, on the real line, you cannot do this trick. That's exactly the. So in the real line, you have to do this equilibrium measure. It is much more non-trivial. This is where we really use that multiple integral representation to get some. First, you have to solve some variational problem. Okay, but here with the Toeplitz terms, everything is absolutely trivial. So you do this, you come to that. And now, so what it is called? There is some name in linear algebra. So I have this matrix, and I can factorize it as z to the minus p minus 1. This is a key issue. So you see, if it were just this, if there were no z to the minus n, so this is where this non-commutativity, non-linearity manifests. If I had only one oscillatory exponent, just like in contour integral, I would be able to just incorporate, to deform the contour so that inside of the unit circle, so that these things would become exponentially small. But then this would become exponentially big. So you have to separate them. That's the point. And you separate it with the help of linearity. Okay. You can just multiply it back and you get this.
They're exponentially growing.
Yeah. So this this now can be incorporated to t minus. This can be incorporated in t plus.
But Luger series give you integer functions which cannot define uniquely.
No.
Or
You I don't. Okay. So what I do? No, you still have this. Of
So
course.
basically, Alexander, this is the Dive-Zoo trick, yes?
Huh?
Basically, this is the Dive-Zoo trick.
Yeah. This is a great trick. So I don't know the dive bike. So this appears of course in the. Now the next is going from T of z to essence. And this is where I'm going to use my assumption about phi. So my S of z is defined as the following way. So this is my original unit circle. Let's consider the smaller circle here and the bigger circle there. This is kind of C1, this is C, this is C2. So I have 1, 2, 3, 4 domains. So these 3 circles divide the plane into the 4 domains. Now, S is going to be my T of Z times, and now it depends on where I am. So if I'm here, I have just identity. So S coincides with T there. And the same is there. But here, of course, when this is C, I multiply S, it is a T multiplied by 1 Z minus N, phi minus N. So this is a, S is T multiplied by this matrix here. And here, it is multiplied by this minus Z to the N, phi 0, 1. So this is, maybe I should, okay, let me even, this is this T, this is this T, this is this T times Z, and this is a T, so this is S. This is S. This is S. And so now we have So now we have, now I am going to write problem for S. So far the transformations are absolutely elementary, so it is the same, everything is equivalent. I can forget about T and think only about S. I can reformulate everything in terms of S. So what is the problem for S? So for S, of course, the problem is this, that now, of course, S is holomorphic minus C1, C2. So I have three contours. And now S plus is S minus GS Z on the contour gamma. So this is a union of those three, it is contour gamma. And at infinity it is still 1. Infinity it is still 1. Now what it is, of course, what is GS? GS is, of course, it is here on this contour. It is what is remaining. What is remaining? So on the unit circle it is this. On the blue circle it is this. And on the green circle it is this, but no minus. So this is a matrix G of S. On the unit circle it is what remains from my original matrix after this factorization. On this it is this, on this it is that. And now, of course, this is where we begin to see that we succeeded in transforming our oscillatory to the exponentially decaying. So this matrix is exponentially close to identity. This matrix is exponentially close to identity. So it is even before doing any so we call it global primitive, even before we're doing any rigorous estimations, you can expect that your solution S would be well represented by the solution of the problem which is set only on the unit circle, and it has so this is a model problem. So we have all the rights to forget about those jumps and just expect that the leading term will be given by this model problem. And of course, this model problem already is explicitly solved. It is basically the scalar problem. I just will write the solution. So the important thing is to factorize phi. And this is where we have, this is a scalar problem. And phi can be factorized by matrix D, which is just, and of course here I should assume that I don't have index. So of course my function doesn't have index. And this is things which appeared in the theory of classical theory of orthogonal. In the Seeger theorem, it is a Seeger function. The Seeger function has a name. And this is P global of Z. P global of Z. It is just this Seeger function to the power sigma 3. So this is diagonal matrix D inverse. And it is just 1 outside and 0, 1, negative 1 inside. Just check it. So this is solution. So this is this is what I expect. And in fact, using this non-trivial fact about L2, boundness of Cauchy, of single Cauchy operator, I can even prove such uniform estimate. Such a uniform estimate. It is true for all z, and rho is something greater than 1, which of course is kind of measures the inner, the outer circle, the outer edges. The proof is absolutely kind of natural. You again consider this difference, this ratio. And what would you have for this ratio? Because my P solves exactly the same problem as S on this, I wouldn't have this jump. For R, I would have only these green and blue jumps. And so the green and blue jumps, it does not matter that they are kind of conjugated with my P. It is identity plus this exponential decay. And so this is, and then using L2 boundness of writing, after that writing this single integral equation for R, and using L2 boundness of Cauchy operator, I can do this. This already would be pointwise uniform. So this is, we need only L2 solution for your integral equations. So this means that we are done with the asymptotic of our Riemann-Hilbert problem. And if you trace back, so what we need to proceed with the proof of the strong criterion, we need now asymptotics for y11 and for y21. And if you trace everything back, you will see that this is this ddb z minus n u minus 1 of z and y21 of z is just minus. Of course, this is the O of rho minus n, O of rho minus n, and since and so now I'm going to use this in my formula. Z minus n, here z minus 1 to pi r, dz. Of course, I have here to replace phi by phi gamma. Phi by phi gamma is 1 minus gamma plus gamma. Okay, so maybe I stop here. So so tomorrow is I continue with this, or I won't, or I just leave it, because now it is already an exercise. It is not very trivial, but it is kind of already everything. We have elementary objects which we have to plug in. We have to plug this into here, then perform indicated operations in a smart way. Well, I will. It still takes some time, but now it is just technical. So, but tomorrow, the main thing would be what to do if we have singularity, if we have a nail, if we cannot go inside and outside, and we have nail. So that would be the opening of lenses. And then we will have not only this global simple solution, but also some local parametrics, which has to be solved explicitly, and then this is where these non-trivial facts about vector geometric functions would show. Thank you very much.
Any questions?
Yes, you have. Huh?
Go ahead.
So you said this row depends on how the distance, I guess.
Yeah.
But it seems that no matter how much you take C1, these will still be decaying, right? So
Yeah, sure. So now it depends on phi. So what is the maximum anomalous?
So you choose this in such a way that phi is the least or something. Or the
Yeah,
lowest.
but again, usually this, you see, this would be kind of the situation which was I probably wouldn't be able to. This is what in the Ising model you have. Something like this. This is the phi for the Ising model. A is real less than 1. And so this is a function, it has jumps. It has A, it is 0, A, 1 over A. And so in the unit circle it is, so that would be the boundaries, how I can proceed. And also this would be the when A goes to 1, that would be interesting situation, what is going on there. So in particular, as I said, this was for this weight, this Siegel formula produced, so the corresponding Topelitz determinant is a so-called magnetization. It is the sigma 0, sigma n. So this is you have statistical mechanical model. You have a present model. What it is a lattice. In each vertices of the lattice, you have either plus 1 or minus 1. Right. And you have so this is a statistical classical space. And in fact, the limit of this correlation function it is exactly magnetization. If it is not 0, it means that you have ferromagnetic. There's a magnetization. You have long order, and so your spins are all kind of even though far away, they all stay. So you have the material is magnetic. If 0, then it is not, and so that was there is a critical temperature when A goes to 1. When you have transition. Yeah, yes, okay.
Can you explain why Topelitz determinants are important?
I think I said. Once again, that's well, it is not a theorem, but the fact, the fact was alive. That's a lot of the object in statistical mechanics is the solvable statistical mechanics.
Okay.
Exactly solvable model. So you see, this is what you have statistical mechanics, and you try to do what? You try to either prove something which is absolutely general for, some universal facts about, or you have some models which you can say a lot. And so this is the theory of exactly solvable statistical or exactly solvable spin quantum models. It is exactly of that.
But is it straightforward, like why Topelitz operators come up and why their determinant tells you something?
No. This I don't know the answer. So this is how the nature is organized. You have to ask him. No, I don't know. Huh? Yeah.
So the initial setup was quite general and relied on functions phi, which were L1.
Originally, yes.
Yeah, I was wondering if we could say something in addition about the Topelitz determinants, if we consider more restricted classes of functions, more regular. I don't know.
So this is what look. This is what we are doing. So if it is just L1, then I don't think if there is any asymptotics behavior, any qualified asymptotic behavior. Already, because already this is the first already the strong figure theorem. It is your phi should be differentiable to some degree. Not okay. Not so it's well. I don't write. So its Fourier coefficients should be summable with okay, so yeah, something like this. So this is a sort of smoothness.
Right.
I don't know how it can be formulated in terms of the function itself. So that is what. But and yeah, so that exactly is my point. That we there's another interesting thing how far you can go and still have for strong security theorems. The answer is it is just that. For Fisher-Hartwig actually it is not. So we have actually we have some condition in that way which I mentioned, but they are not ultimate. At least not good. So there are many, so that's.
I guess I have a question on the history part.
Yes.
Why is the name Riemann there?
Huh?
The name Riemann, you said
The
that?
name?
Riemann. Right?
Riemann. That's a great question. Again, so of course it is a great style. You have to read classics, even if you don't know German, So this is but I don't do it. But I rely on my colleagues who did. And so again, you can. There is this book I mentioned. Maybe I not. Anosov and Bolibrook. In fact, it is called the Riemann-Hilbert Program. The book written by Anosov and Bolibrook. And the explanation, and I read just their preface, and I read just in their book. So according to their references, according to their, it is just Hilbert himself sort of called it Riemann. Riemann was dead, I believe, by that time already. Because he says that it was exactly what Riemann formulated, what Riemann suggested to think about. Kind of reconstruction of the function out of its monodromy properties. So you have function, single-varied functions. Then how you can reconstruct? You have to know poles. So this is the reconstruction of functions out of its pole structure. This is a standard. This is it. Then you have more complicated situations. The function is not single-varied, so it means that it has some monodromy properties. So it is defined on exactly on not simply connected domains. So it would have properties, and he kind of formulated in some way, of some systems. I never saw it. So this is why so it was not. I believe that Riemann did not formulate it as a problem for Fuchsian systems. That's probably the only difference.
Yeah, Riemann's work is all translated, so there's no excuse, I'm afraid. The whole work.
Yeah, I know. Yeah, this is no excuse. You're right.
The French one's about 8 years old.
No, you're right. Not very happy with it. The only excuse is to say that I cannot read.
Let's make the speaker again.